Hello guys, welcome once more to another video on our YouTube channel. So in this video we are going to be looking at the 21 days integral challenge that I did in the month of March. So in the month of March this year, I challenged myself to do an integral challenge which was to run for 21 days. So this integral challenge started fully on the 8th of March and it ended on the 28th of March. But on the 7th of March, I had to alert the general public that I am going to be starting this integral challenge on the 8th of March. So the main objective of this integral challenge was to integrate some functions in some nice ways. Okay, so that was the main aim, and we all know that from the beginning, the primary objective of the MAFA organization is to promote the study of mathematics in schools and in universities. So for those of you who are just joining us in this YouTube channel, endeavor to subscribe to the channel, turn on your notifications so that whenever content is being uploaded, you will be notified to come and watch. After watching the video, endeavor to like the video and share the video. It is going to help us to gain more influence here on YouTube. Alright, so day 1 of the integral challenge was on the 8th of March, like I precised earlier. And on this day, the integral that was supposed to be done was the integral of dx divided by e to the x plus 1. That is integrating the function 1 over e to the x plus 1 with respect to x. So like I said, there are many ways of integrating functions, but this integral challenge was to unleash some specific ways and some very unique ways of integrating such functions. Okay, so it does not mean that the method I'm going to use here, if you use a different method and get a different answer, your answer is wrong. No, your answer is correct provided your method was correct. Remember, this is an indefinite integral, and indefinite integrals, we don't end up with the same answers if we use different methods. But once it becomes definite, we must end up with the same answer no matter the method we use. So let's get started with this. Alright, so the first thing to do is that we multiply the numerator and the denominator of this integrand by e to the negative x. Doing that, we try to keep the numerator as e to the negative x, and then we multiply the e to the negative x into every term in the denominator. So, and we get e to the negative x divided by 1 plus e to the negative x. So from there, integrating 1 over e to the x plus 1 with respect to x is equivalent to integrating its identity, which is e to the negative x divided by e to the negative x plus 1 with respect to x. Now it is clear that once we differentiate the denominator, we get something in the numerator, so that is our u substitution. So we are going to go ahead and let u to be e to the negative x plus 1, which is a denominator. We differentiate both sides with respect to x and we multiply all through by the dx. In fact, our du will give us negative e to the negative x dx. So the integral becomes the integral of negative du on u. Why? Because the e to the negative x dx that is in the numerator of the previous integral, if we find it from our derivative, it's just going to give us negative du. So from there, we can just replace, and we replace the denominator with u, and then we integrate standardly. We get negative ln of the absolute value of u plus k, where k is a constant of integration. But we know that our u is e to the negative x plus 1. It therefore means that that integral is negative ln of the absolute value of e to the negative x plus 1 plus our constant of integration. Nevertheless, even without the absolute value, you are still correct, because the function e to the negative x plus 1 is always positive for all values of x that belong to the set of real numbers, which is the domain of definition of that function. So that is that for this integral, and that was that for day 1. Alright, now day 2 of the integral challenge was the 9th of March, and the integral that was to be done was the integral of 1 over sine x with respect to x. So very nice properties were being used, as 1 over sine x can be written as sine x divided by sine squared x. These functions are well defined. Sine x cannot be 0, that's why we can multiply top and bottom by sine x. Okay, so from there we now know that the integral of 1 on sine x dx will be equivalent to the integral of sine x on sine squared x dx. Now, since we know the identity of sine squared x as 1 minus cos squared x, we just rewrite the integral that way. Now, if we identify keenly, we are going to see that once we differentiate cos x, we are going to get a relationship with what is in the numerator of our integral. So that becomes our u substitution. So our u substitution is v equal to cos x. We differentiate both sides, we get the v to be negative sine x dx. Now the sine x dx is in the numerator, is going to be negative dv. So we carry that and paste in our integral, and we get the integral of negative dv divided by 1 minus v squared. Now this is a standard integral, which is tangent inverse of v, then plus our constant of integration with the negative sign. So if you want to use an alternative method, you can use integration by partial fractions. So you partial fract 1 over 1 minus v squared, and then you integrate the partial fractions separately, and then you combine them together. Nevertheless, we know the definition of tangent inverse of v, we just need to replace it. But since we began with the variable x, we cannot end with the variable v, since we are still dealing with an indefinite integral. So we need to convert back our v to x, and our v was cos x actually. So it means that this integral is negative half the ln of the absolute value of cos x plus 1 divided by cos x minus 1 plus a constant of integration. Okay, day 3 of the integral challenge was on the 10th of March, and the integral to be done was the integral of 1 divided by dx with respect to x. Now this integral was very bizarre, but anyways, we are going to see the little trick behind it. You can pause the video and try to see if you can integrate this function. Okay, if you cannot, write your comments in the comment section. But nevertheless, we are going to see how the function can be integrated. Okay, now looking at this function very well, we know that we have to integrate with respect to a variable, which is x. The numerator is dx, the denominator is dx. So the dx in the numerator has to stay, because we need it there, because we have to integrate with respect to the variable. So the dx in the numerator has to stay. So having that in mind, it therefore means that the d in the denominator is simply a constant. Okay, so dx is in the denominator, but it is not equivalent to the dx in the numerator, since the dx in the numerator has to be there, since we are integrating, since when integrating we have to integrate with respect to a variable. So the d and x in the denominator are like products, okay, where the d is a constant and the x is a variable, since we have it in the numerator that we are integrating with respect to. And integrating that, we just get what you have seen there already. And further explanations, like I said, we cannot cancel out the dx terms, since we're not, because cancelling out the dx terms, we are going to integrate 1, and integrating 1 will yield you nothing, because you are integrating with respect to no variable, so we cannot cancel out the dx. And with that said, that d in the denominator must be a constant. Okay, so I think in that period I was very motivated. In fact, that very day I was actually very motivated, and I tried to relate the topic integration with somehow a real life situation. Okay, somehow it is a motivational integral, like it is written. So this motivational integral says that the integral from hard work to patience is actually integral of hard work to patience of studying with respect to time is equal to success. So we all know that integral simply means summing. Okay, that's their integrating simply means you are doing a certain sum. So from there we can now say that since the integral from hard work to patience of studying with respect to time is success, it means success is the sum of the hard work that you do while studying. So you have to be hardworking, you have to be patient while studying. Now actually sum from hard work to patience, you have so many elements within. There is also determination, prayers, motivation, whatsoever, but that's what we have. Okay, so studying is a function, and the interval from hard work to patient contains, like I already said, prayers, determination, and all the positive factors applied in the studying process. So studying is a function means that we all know what a function is. A function is a mapping that takes elements from one set to another. The first set is called a domain, the second set is called a codomain, and we should note that to be called a function, the mapping must be either a one-to-one mapping or a many-to-one mapping. In fact, it is a mapping. In subsequent videos, I'm going to give you guys more motivational talks regarding mathematics. Alright, so get inspired to study. Okay, so let's proceed with what we have. We have day 4, which was March 11, and we were supposed to integrate x e raised to the power x with respect to x. So the best thing to do here is to use integration by parts, which we are going to prove the formula. Now, integration by parts is a very unique and very technical way of integrating functions. In this process, we actually use the process provided we have no substitution to make. If we have no u substitution to make, the first thing to think about is integration by parts. Okay, so how then is this process being applied? In fact, if you have a function which is a product of two functions, so my function y is a product of two functions all in the same variable, which is x. If I ask you to differentiate this function, we need to apply the product rule. It is a rule in differentiation. So the product rule says that the derivative of y with respect to x is equal to u times the derivative of v with respect to x plus v times the derivative of u with respect to x. So from there, it means that we can actually integrate all through, because the equality holds, integration is distributive over addition, and the functions that we are integrating are well defined. So from there, integrate dy, integrate u dv, and add it to the integral of v du. So from there now, integrate dy, you get y, integrate u dv plus integral of v du. So from there, we have to find the integral of u dv, which is actually what we integrate when using integration by parts. So the integral of u dv becomes y minus the integral of v du. But what is our y? Our y is uv. Okay, that's what we let it to be in the initial at the beginning. So the integral of u dv becomes uv minus the integral of v du, and this gives us the integration by parts formula. So in this case, we have to let one portion of our integral, that's one portion of our integrand, to be u, and another portion to be dv, because you are integrating u dv. The portion you let to be u should be the portion you can easily differentiate, and the portion you let to be dv should be the portion you can easily integrate. So clearly here I'm going to let my u to be x, though I can easily differentiate and integrate my u and my dv in this case, because I'm going to have x and e to the x dx, or e to the x and x dx. But I'm going to tell you why we are letting u to be x. So we let u to be x, it therefore means that our du will give us dx, and then we let dv to be e to the x dx, meaning the remaining portion of the integral, and then to get v we have to integrate. Now integration by parts formula says that this integral is equal to uv minus the integral of v du. So our u is x and our v is e to the x minus the integral. Our v is e to the x and our du is dx. If you integrate e to the x, you still get e to the x, but you have to add your constant of integration. You can now combine the you can actually factorize e to the x from the first two terms, and you get this integral to be e to the x times x minus 1 plus k. Like I said, I'm going to tell you guys why I never used my u to be e to the x, knowing fully well that I can differentiate it easily. Now this is the reason. If I let u to be e to the x and my dv to be x dx, you see that I'm going to integrate x dx and I'm going to get x squared divided by 2. When you do the manipulations and replace back in the integral, you're going to find out that you're going to be integrating now x squared over 2 times e to the x. You see the power of x has increased, but initially we want it to decrease. Okay, so that is why I did this substitution. But there are mnemonics you can use to be able to identify which substitution to let to be u and which substitution to let to be dv. I think there is a mnemonic called like, but I'm going to explain that in the subsequent videos. Okay, day 5 of the integral challenge was March 12, and we were supposed to integrate 1 divided by x squared plus 2x plus 2 with respect to x. So the very first thing when you see such integrals is to complete the square of the denominator. Completing the square of the denominator means I should write it as the sum of 2 squares, okay, or the sum of maybe a perfect square and a certain number. In fact, you can always write numbers as squares because you have the square root property. So I'm going to complete the square in a very unique way, which is a very important method you have to know in mathematics. X squared plus 2x plus 2 can be written as x squared plus 2x plus 1 plus 1. I wrote x squared plus 2x plus 1 because it is already a perfect square, okay? So I splitted 2 to give me 1 plus 1, and addition is commutative. So from there, the first 3 terms in the denominator gives me the perfect square x plus 1 all squared, and then I need to add the remaining one. So it therefore means that the integral that I am doing is equivalent to the integral of 1 over x plus 1 all squared plus 1 with respect to x. Now we need to do a u substitution, not actually a u substitution. Anyways, you just need to relate your x here with a new variable. So we are going to take x plus 1 to be equal to tan theta. If we differentiate both sides, we get the x to be equal to sec squared theta d theta. This integral becomes, the numerator is dx, which is sec squared theta d theta, and the denominator is x plus 1 all squared, which is tan squared theta then plus 1. But we know that tan squared theta plus 1 is sec squared theta, which in turn cancels with what is the numerator, and we are just left with the integral of d theta, and this gives us theta plus a constant of integration. But we cannot begin with the variable x and we end in the variable theta in an indefinite integral. So we need to look for theta in the in our substitution here, which says x plus 1 is equal to tan theta. From there, our theta is tan inverse of x plus 1. So with that, it means our integral is tan inverse of x plus 1 plus a constant of integration, and that's it. Okay, so day 6 of the integral challenge was March 13, and on this day we're trying to see how we can relate mathematics with chemistry. So we're trying to give a relationship between the concentration and the time of a reaction whose order is 1. That's the overall order is 1. So we considered a reaction where we are moving from the reactant to the product. The reactant was, the particle was capital A, and small a is the number of moles of the reactants in a balanced chemical equation, and the product was capital B, and small b is the number of moles of the product. So we're trying to relate the concentration of this particular reactant with respect to time in this reaction whose order is 1. So first we have to write the rate law of this reaction. So the rate law says that the rate of any chemical reaction is always proportional to the concentration of the reactants raised to, that's in fact the product of the concentration of the reactants raised to their partial orders. But since in this case we have only one reactant, which is A, we don't deal with the product, we deal only with the reactants. Okay, so here we have only one reactant, which is A, and the partial order is small n becomes the overall order of the reaction. Now, since we are talking of a proportionality sign, there you can see an equality sign because we have introduced the constant of proportionality, which is in turn the rate constant of the reaction. So the rate is equal to K times the concentration of the reactant A raised to the power n. But since we are studying a specific case, which is a reaction whose order is 1, it means that n is equal to 1. And with that, the rate of this chemical reaction becomes the product of the concentration of the reactants and the rate constant. But the rate of a chemical reaction is actually the change in the concentration of the reactants with respect to time. And since the reactant is actually in fact the concentration of the reactant is decreasing as time goes by, because we are taking the forward reaction. Okay, so if you begin with a certain initial amount of the reactant, as time is going, all the reactants or the reacting molecules will be converted to products. So it's actually a decay curve. That is why there is a negative sign in front of the change. So dA on dt simply means the change in the concentration of the reactants with respect to time. So we equate it to the rate constant multiplied by the concentration of that reactant at any time t. Alright, so from there now we can see that this is actually a first order variable separable differential equation where we can separate the variables and we integrate. This is where integration comes into play. Alright, so separating the variables, we obtain this, and then integrating both sides of the equation, we obtain this. So it means that the ln of the concentration of the reactants is equal to negative kt plus c, where c is a constant of integration. Now we can impose some initial conditions to the system to be able to get our constant of integration. So we can assume that initially, that's when time is equal to 0, the concentration of our reactant is actually the initial concentration, which is the concentration at t equal to 0. So with that, we just need to replace it in the previous equation, replacing t to be 0, the term kt turns to 0, and we are left with c to be the ln of the concentration of the reactant. So with that, we can replace back the value of c in our differential equation that was already solved, and we have the ln of the concentration of the reactants to be negative kt plus c, which is the ln of the initial concentration of the reactant. So from there, we can now bring like terms together and we find the concentration of the reactants in with respect to time, okay, at any time t. So if you look at this, you clearly see that it is kind of decay. Those who are physics students, if you have done radioactivity, you identify that this is kind of the equation of a decay curve. Alright, what about k? Our k is the rate constant, but we can find it relating it with the half-life of the reaction. Okay, so k is the rate constant, like I said, and we have to find the expression of k by also imposing some initial conditions to the system. So when the time is equal to t half is actually the half-life, which is the time taken for the concentration of the reactant to decrease to half of its initial value. Its initial value is its initial concentration, which is the concentration at 0, then divided by 2 will give us the concentration at the time t half, which is a half-life. Okay, so with that, we can replace that concentration in the equation that we have had above, and then we take like terms together and we find k. So our k gives us ln 2 divided by t half. So here we have gotten k, which is a rate constant for an equation for a reaction that is first order with respect to the reactants, and here we just generalized it and said we have just one reactant. So that's k, the rate constant, ln 2 divided by time taken for the concentration to decrease to half of its original value. Okay, so March 14 was the next day, and it was actually the International Day of Mathematics. We also call it the Pi Day. So I actually something on that day which is going to be a little bit lengthy if I try to explain, but since it was a pi day, I was trying to relate the number pi with the factorial function, the gamma function, the Gaussian integral, and so on and so forth. So it is long to explain. I'm just going to leave it. If you want to take a snapshot of what you see, you can screenshot what you see. If you need the PDF actually, or in fact yes, if you need a PDF of this presentation, you can just get to me. My number is not on the screen, but I'm going to give you guys some informations in the description of this video and also in the comment section. So if you want to get to me, you can get to me and I can share the PDF with you. Okay. Okay, so that very day, though we had to celebrate the International Day of Mathematics, but it did not stop me from continuing my 21 days integral challenge. So day 7 was the 14th of March, and that day we're trying to integrate the ln of x to the power 2023 from 0 to 1. So we are now talking of definite integrals. Okay, so there is a note here that this particular concept I'm about to explain is to be taken seriously by students in professional schools, specifically engineering students, also students that are preparing for engineering entrance examinations, and also advanced level further mathematics students as well as teachers. Okay, so to integrate this, I decided to give a general integral. Okay, so we define the integral I of n to be the integral from 0 to 1 of ln x raised to the power n. So when we integrate this, we can now integrate what we have, which is simply gotten by replacing n with 2023. So to integrate this, we actually use the concept of integration by parts. So using integration by parts, we see that here we have ln x to the n dx, but there is no other portion of the integral again. So there is an invincible one that we have to see. Okay. Nevertheless, I'm going to let my du to be equal to my u to be ln x to the n, and I differentiate both sides. Differentiating ln x to the n entails dropping down the power, which is n, differentiating ln x, which is 1 on x, and then multiplying it with the very function to the n minus 1. That's, they say the x is lacking, hope you saw it. And then my dv is equal to dx, so my v is equal to x. Now this integral becomes uv minus the integral of v du. My uv is x times ln x to the n from 0 to 1 minus the integral of v du. There is an n that is a constant, it does not depend on x, so we pull it out of the integral. So we have the integral from 0 to 1 of my v is actually x, that's it in the numerator, then du becomes ln x to the n minus 1 all divided by x, because the n is already out. From there we try to simplify and we use the limit definition of this this x ln x to the n from 0 to 1, because the number 0 is not in the domain of definition of ln x, so we cannot be plugging in 0 there, so we need to use the limit definition. Okay, in fact we can say it is an improper integral. So with that, using the limit definition there, we have that you're going to take the limit as in fact, if we plug in the upper limit, which is 1, we have 1 ln 1 to the n. Ln 1 is 0, so the upper limit is 0. If you plug in the lower limit, you're going to actually be taking the limit as x tends to 0 from above of x ln x to the n, but it tends to 0. It is a standard limit, so that first portion of my integral disappears and I'm just left with negative n. Now this new integrand here, you see that the x cancels with the x in the numerator. Okay, so you just have the integral from 0 to 1 of ln x raised to the power n minus 1. Now if you clearly identify, you see that the integral from 0 to 1 of ln x to the n minus 1 is I of n minus 1. There is a negative n that is multiplying it. So with that said, we can now do some backward substitutions. Okay, we move backwards and then I try to identify a kind of telescopic something. Okay, so from there, since we have I of n to be negative n I n minus 1, it therefore means I n minus 1 is negative into n minus 1 times I n minus 2. Just check the subscripts on the left hand side and on the right hand side and see what is happening. So you clearly see that we can now replace our I n minus 1, which is what is circled, back into I n. So doing that, we are going to get our I n to be negative n times this other portion. Okay, so from there, if we do backward substitution n times, we are going to arrive at all of this. So we are just going to be doing backward substitution till we arrive I0. If we simplify perfectly well, you see that the negative signs are all in front of the linear terms in terms of n. So we have negative n minus 1, negative into n minus 2, right down till negative 1 times negative 2. So you're multiplying those negative signs n times. So it's going to be negative 1 raised to the power n. Now removing all those negative signs, you still be left with n into n minus 1 into n minus 2, right down to 2 times 1. But n into n minus 1 into n minus 2, right down to 2 times 1 simply identifies n factorial. That's the definition. Then we have I0. So let's now look for I0. I0 is simply the integral from 0 to 1 of ln x raised to the power 0. The ln x raised to the power 0 is 1. So from there, we integrate the x, we get x from 0 to 1. Feed in the upper and lower limits, you get 1. And from there, we get I of n to be negative 1 raised to the power n times n factorial. Now, our case is actually the integral from 0 to 1 of ln x to the 2023. So we are looking for I of 2023. So it should give us negative 1 raised to the power 2023 times 2023 factorial, which is negative 2023 factorial. Hence, we can conclude that that integral is negative of the factorial of 2023. Okay, day 8 of our integral challenge was March 15. Interesting integrals were coming up. I was being inspired, and here we want to integrate the square root of x plus the square root of x plus the square root of x right down till infinity. Means we do this forever, integrate from 0 to 1, and we have to leave our answer in terms of phi, which is the golden ratio. So the first thing to do is that I'm going to let the integrand to be something, and then I try to look at some properties of such functions. Okay, so y is equal to the square root of x plus the square root of x plus the square root of x, and so on and so forth. Now if you look keenly, we are going to identify that, or in fact, if you square both sides first, we are going to have y squared. You see that the bigger square root will just walk away, and we are going to left with the x at the beginning. But now, in fact, when the bigger square root walks away, we are going to be left with its interior, which is x plus the square root of x plus the square root of x plus square root of x, and so on and so forth. But if you look keenly, since this sum of nested square roots are actually infinite, it means that this portion which is within here is simply our y. It is still y, it has not changed. Okay, if you look at it keenly, because the sum of those square roots are infinite. So removing the first portion does not change anything. So it therefore means that our y squared will be equal to the x then plus the y. So from there we can get y by subtracting everything to the on both sides of the equation, and then we solved for the quadratic. We solve for y in this quadratic equation. Our y will give us negative b, which is 1, plus or minus the square root of b squared minus 4ac, all divided by 2. Doing that, we get this quantity. Okay, but now there's a problem with this plus or minus. We need to choose one. So let us go ahead to choose. How then do we choose between which one is plus or which one is minus? Now remember that our x is in the interval 0 to 1. Okay, now this y has two values according to what we see here. We have 1 plus the square root and 1 minus the square root. But since the function y itself is the square root of some things, it therefore means that it is a positive function, because the square root of everything, of anything, when that thing is positive, is also positive. So it therefore means that if I am choosing a correct function here, it should be a positive function. So we know that since x is in the positive interval, then that is x is between 0 and 1, 1 is included. I'm not trying, in fact 1 is included. I'm trying to remove 0 from this case. Okay, I'm just trying to remove 0 from there. 1 is included, because if you have x to be 0, then this square root is just going to give you 0, and you'll be integrating 0, which will give you 0. It does not make sense. So that's why I am removing 0 from the interval, and 1 can be included. So from there now, we clearly see that if we multiply all through by 4, we have 0 is less than 4x less than 4. If we add 1 everywhere, we have 1 is less than 4x plus 1 less than 5. Then we can now take the square root and we arrive where I have arrived. So from there, we can clearly see that if we consider the 1 less than or equal to the square root of 1 plus 4x, we see that it is less than 0. Okay, so 1 minus the square root of 1 plus 4x will be less than 0. Less than 0, and we know fully well that y is supposed to be greater than 0. It therefore means that the negative portion, the 1 minus that square root, is not going to be taken. So we are just taking the 1 plus the square root, because our y is supposed to be positive. So from there, we have gotten the correct function y. So y is equal to integral from 0 to 1 of 1 plus the square root of 4x plus 1, all divided by 2. So we are left now to integrate this function. So I leave that to you. I'm just going to display the steps. Okay, so it should be noted that 1 plus the square root of 5 divided by 2 is the golden ratio. So it means this integral is 5/6 of the golden ratio. Okay, integrals were coming up and the integral challenge was becoming very interesting. So day 9 was March 16, and the integral that we're supposed to do was the integral from 1 to 2 of 2 times the square root of 2 minus x, all divided by x with respect to x. So I think I was once solving equation from a regional mock examination of further maths, and I came across something like this, and I decided that okay, this integral is very technical, so why don't I use it as an integral challenge in my integral challenge? So that's what we are going to be doing. So we are going to use a substitution, which is actually x equal to 2 sine squared theta. So this substitution, it means we have to differentiate both sides. If we differentiate 2 sine squared theta, we get 2 into, we now differentiate the sine squared theta, we have 2 sine theta cos theta. So from there now we have that if x is equal to 2 sine squared theta, it means our sine theta is equal to x divided by 2, because x is in a positive interval from 1 to 2. In fact, it works. Specifically in this case, only the positive square root works. The negative square root does not work. So with that said, it therefore means that our theta is sine inverse of the square root of x divided by 2. So we now change our since it is a definite integral, we now change x to theta. So x begins from 1 to 2. It means theta will be sine inverse of 1 over root 2, which is pi ln 4. And then when x is 2, our theta is sine inverse of 2 on 2, which is pi ln 2. And clearly in the interval pi ln 4 to pi ln 2, the sine function is positive. So we take only the positive square root. Alright, so from there now, x being equal to 2 sine squared theta, okay, it means that our sine squared theta is x divided by 2. Sine squared theta being x divided by 2, and we know fully well that cot squared theta is cos squared theta divided by sine squared theta. It therefore means that our cot squared theta will be also equal to 1 minus sine squared theta over sine squared theta, because our cos squared theta is 1 minus sine squared theta. So from there, we have sine squared theta as x divided by 2. We just need to replace it where it is supposed to be, and then we try to simplify, and then we clearly see that our cot squared theta is 2 minus x divided by x. It therefore means that cot theta is the square root of 2 minus x divided by x. Positive square root because of our interval. The interval is positive, so, and our theta as well. So the positive square root works, not the negative square root. Alright, so from there now, we just replace back everything in our integral, and everything simplifies to be nice. We have the integral from 1 to 2 of 2 the square root of 2 minus x on x. With respect to x, though I missed out, I never wrote the x there, it's supposed to be there, please. Equal to, now we just need to replace the value of the x, which is 4 sine theta cos theta, okay, as we can see in the very first line of our substitution. But now we have to multiply it with the 2 that is in the integral to give us 8, that is it out. Now this square root here has already given us cot theta, but this very dx, we need to write the other portion, which is sine theta cos theta d theta. Now if you try to simplify, we know that cot theta is cos theta divided by sine theta. We now see that the sine thetas cancel, and we get integral from pi ln 4 to pi ln 2 of cos squared theta d theta. Now we have to convert cos squared theta to cos 2 theta, and then we easily integrate. So that's all we have to do. We fit our limits of integration, and then we simplify to get that integral as pi minus 2. Okay, day 10 of our integral challenge was on March 17, and there was a code that I produced. It says the result of an indefinite integral is independent of the method displayed, provided the right substitutions are used. Alright, so in this day, on this day, we're to integrate 1 divided by 1 minus sine x with respect to x. So many methods could be used here, but I used a specific method. I don't know if I used 2 methods, but anyways, as we go, we are going to see if I used more than 1 method. Alright, so first of all, what I did was that I did a kind of rationalization, okay? So I multiplied the top and the bottom of the same integrand by 1 plus sine x. The numerator becomes the very 1 plus sine x, but the denominator is like you're multiplying 1 minus sine x with 1 plus sine x. Is just a difference of 2 squares, which is 1 minus sine squared x. Now we know that 1 minus sine squared x is cos squared x, and knowing fully well that if we differentiate cos x, we are going to get sine x. In fact, first of all, we are going to split the integral into 1 divided by cos squared x plus sine x divided by cos squared x. The 1 divided by cos squared x is sec squared x, so that's what we are integrating. Now standardly, we know that we can integrate sec squared x. It's just going to give us tan x, right? Because when we differentiate tan x, we get sec squared x. So obviously if we integrate sec squared x, we should get tan x. Now the problem is the other part of the integral, which is not actually a problem because it's kind of derivative around. If we differentiate cos x, we get the numerator, so we just have to manipulate, so that becomes our u. So using a u substitution, we let u to be cos x. That's for the second portion of the integral. Our du becomes negative sine x dx. It therefore means that that integral, remember that the numerator is kind of sine x dx, so if you look for it here, you have negative du. So that portion, we can integrate it. You're going to have negative du on u squared, which you can write it as negative integral of u to the negative 2 du. Then we use the first fundamental theorem of calculus to integrate that, and we get u to the power negative 1, which is 1 on u, and 1 on u is actually 1 on cos x because u is cos x. Now we now clearly see that this integral is tan x, which is the integral of sec squared x, then plus now 1 on cos x. 1 on cos x is sec x, then plus the constant of integration. So this was a very nice method that I tried to come out with. All right, so another method was using half angle identity, where we know that whenever tan x is x on 2, whenever t is tan x on 2, our dt will give us half sec squared x on 2 dx. Doing manipulations, we know that from there we can get dx as 2 dt on 1 plus t squared. Now what about 1 minus sine x? Should be 1 minus 2t over 1 plus t squared, because when t is tan x on 2, our sine x is 2t on 1 plus t squared. So from there, if we simplify perfectly, we arrive where I am, and then now integrating it is just equivalent. So we need to replace the x with what we have. We replace the denominator with what we have, and then we integrate. Normally we are going to get 2 divided by 1 minus t plus a constant of integration. But we know that t is equal to tan x on 2, so we have 2 over 1 minus tan x divided by 2 plus a constant of integration. So I used these two different methods and I had two different answers. That is why I now reasoned out and I said the result of an indefinite integral is independent of the method displayed, provided the right substitutions are used. So I was now posed with a little bit of challenge. In fact, I was trying my best to see if I can relate tan x and sec, if I can relate tan x plus sec x back to the half angle identity. So tan x plus sec x is actually sine x plus 1 divided by cos x, and then you can replace sine x with its identity in terms of tan x on 2. You also replace cos x with the same thing, and then you try to simplify. You're going to get 1 plus t on 1 minus t, which is 1 plus tan x on 2 on 1 minus tan x on 2. So I was now posed with a challenge to see if I can actually prove that 1 plus tan x on 2 is equal to 2. Why am I saying so? I'm saying so because if I do tan x plus sine x, I get 1 plus tan x on 2 divided by 1 minus tan x on 2. But now, when I integrated it using the half angle identity, I got 2 divided by 1 minus tan x on 2. So they have the same denominators, so their numerators must be the same. So that was now a challenge. I thought if it can be proven. So tell me in the comment section, give me your reaction in the comment section. Alright, so the 11 of the integral challenge was March 18, and the integral was the integral of e to the x times sine x. I cannot even remember the method I used here. I don't know if I used integration by parts or there were other things that I used, but anyways, we are going to see the solution. Alright, so we have I to be the integral of e to the x times sine x dx. So here, if we use integration by parts, we're actually going to use integration by part 2 times. Okay, so this is how it goes. Okay, and I'll see first method I try to relate with complex numbers. Remember that the theme of these integrals from the previous day was that the result of an indefinite integral is independent of the method displayed, provided the right substitutions are used. So let's come back here. Our sine x is actually the imaginary part of e to the ix, because e to the ix is cos x plus I sine x. So sine x is its imaginary part. So from there, it means that this integral is actually the imaginary part of e to the x times e to the ix, because we have just replaced the sine x with the imaginary part of e to the ix. Now we know fully well that the e's have the e's are a common base, so we have to add the powers and then we factorize the x. So integrate e to the power a linear function, you have 1 divided by, you differentiate x into 1 plus I, you're just going to get 1 plus I because it's kind of a constant, and then you multiply it with a very function, then now plus a constant of integration. I am adding a constant of integration z because I'm dealing with complex numbers here. Okay, so from there now we can now simplify, knowing fully well that we have to take the imaginary part. So we can have rationalized 1 divided by in fact, this e to the x is actually cos x plus I sine x, that's e to the ix. Now 1 divided by 1 plus I is 1 minus I on 2 after rationalization, but now there's still an e to the x that's in the numerator. So then we now simplify and then we take the imaginary part only, we arrive at this integral. So it is very short using complex numbers. I don't know if I used integration by parts. Okay, I used it twice. Okay, and this is how it goes. We let u to be sine x, our du gives us cos x dx, and then we let dv to be e to the x dx, our v gives us e to the x. Now our integral by integration by parts says that we have to take uv minus the integral of v du. So uv is this minus integral of v du, which we have to integrate this by parts again. So we now call it j. Now there we have our I to be e to the x sine e to the x sine x minus j, where we are going to use integration by parts to integrate j. Okay, so how do we do? Same process. We let u to be cos x, our du is negative sine x dx, our dv is e to the x dx, our v is e to the x, our j is same story, uv minus the integral of v du. So we just need to plug in there, and then we are going to identify that in the integral j, okay, in the integral j there is I inside. So at the end of the day, this is actually j, not I. So this integral here is actually j. So j is e to the x cos x plus integral of e to the x sine x, which is e to the x cos x plus this integral originally is I. So from there we have now a very unique property. From there our I, which was e to the sine x minus j, becomes e to the sine x minus the j, then plus a constant of integration. So from there now we can add the I on both sides of the equation after multiplying all through by the negative sign, and then we divide both sides by 2, and then we see come back to where we what we had when we used complex numbers. Alright, the 12th of the integral challenge is actually finding the first 3 digits of a password. So this question kind of went viral some time back, but I tried to use something else. Okay, so I tried to use the methodology of the question itself to define a new question, somehow still related to the original question that came out some time ago. So we are to integrate from -1 to 1 of x squared sine x plus 2 times the square root of 1 minus x squared with respect to x. So the 12th was on March 19. So doing this, we define this integral like this, and then we have separating the integral, taking x squared sine x and multiplying it with the square root, and then adding it to 2 times the square root of the integral from -1 to 1 with respect to x. Now this portion of the integral, clearly we see that if the integrand is f of x, we can do f of negative x, meaning we check the parity of this function. So f of negative x is found by replacing x with negative x in the f of x. So doing that, we have negative x squared sine x, the square root of 1 minus x squared, which is negative f of x. It therefore means that the parity of this function is odd. That the function is an odd function, and since it is an odd function, it is a definition that the integral from negative of a bound to positive of that bound is equal to 0. So with that, we are just left with the integral of 2 times the integral from negative 1 to 1 of the square root of 1 minus x squared. This is where things become very interesting. Now, clearly, if we plot the graph of the square root of 1 minus x squared, you clearly see that on the xy plane, it is simply a semicircle whose radius is 1, and the semicircle lies above the x-axis, okay, because it's a positive square root. So the integral from negative 1 to 1 is simply the area under the graph of that semicircle, and the area is simply given by, how do we find the area? Pi radius squared. Now the radius is 1, you square it, and then you divide it by 2 because it's a semicircle. So we have this integral to be 2 times pi ln 2, which gives us pi. But nevertheless, let us see how we can actually integrate it, not using the concept of area. Okay, so we have 2 times integral from negative 1 to 1 of the square root of 1 minus x squared. We can clearly see that this function is an even function by the property that g of negative x is equal to g of x, and it is the definition that since it is an even function, then the integral from negative 1 to 1 is 2 times the integral from 0 to 1, but there's a 2 outside there already, so we now get 4. Now, how then do we integrate this? We let x to be sine theta, our the x gives us cos theta. Now we have to change the bounds. X begins from 0 to 1, so theta is from 0 to pi ln 2, because theta is sine inverse of x, so we have sine inverse of 0, 0, sine inverse of 1, pi ln 2. So the integral becomes 4 times integral from 0 to pi ln 2 of the square root of 1 minus x squared times dx, and our dx is cos x. But the square root of 1 minus x squared is the square root of 1 minus sine squared theta, which is cos squared theta. Now, the square root of cos squared theta is actually the absolute value of cos theta. But anyways, it is in a positive interval. In fact, it is an interval where cos theta is positive, so you just have cos theta. Multiply it with a dx, which is cos theta, we get now cos squared theta. We convert it to cos 2 theta and we integrate. At the end of the day, we still get pi. So it means this integral here is pi, and the first 3 digits define my phone's password. Okay, the 13th of the integral challenge was on March 20th. So here we are integrating a nested square root, but this time around it is a product of square roots, not a sum of square roots again. So we do the same thing. We define y to be that function. We square both sides. You see, when you square, the x that begins leaves the square root, and then now you're going to be left with the square roots of the rest of the other portions. And we still identify that the square root of the rest of the other portions is still equivalent to the function y. So it therefore means that our y squared will be equal to x times y, meaning y squared minus x times y is 0. We can factorize y and we have y equal to 0 and y equal to x. But now it's clear our y cannot be 0 because we cannot be integrating a null function. So from there, we have now to integrate x from 0 to 1, which is just x squared on 2, from 0 to 1, which gives us half. Okay, so this integral is equal to half. Is there any other alternative path? Yes, there is. Let us proceed this way. Alternative part, we have to see that from indices, okay, this first x here will be raised to the power half because it is actually inside one big square root. But the next x now is inside two square roots. It's inside the first bigger square root and then the second square root. So you need to multiply the halves together to get 1/4. The third x here is inside 3 square roots, the bigger one, the second, and then the third. So you have to multiply the halves to themselves 3 times, and so on and so forth. Now clearly, since you're multiplying the x's have the same basis, so you have to add their powers. Okay, so you have half plus 1/4 plus 1/8 and so on and so forth. So you're simply summing from n equal to 1 to infinity of half raised to the power n. Clearly we see that this sum is a sum of a geometric progression whose first term is half and the common ratio is half. So we can find the sum to infinity. So at the end of the day, it gives us x, and integrating, we know how to integrate x squared on 2, then we fit, and then we get our x, that integral, to be equal to half. Okay, day 14 of the integral challenge was March 21, and on this day the integral was pretty easy, but there was a specific property that I was trying to bring out. Okay, so we have to integrate this. So the first thing to do is we do long division, and to do long division, I ran away from long division and I used a very important property of mathematics. Now x divided by x plus 1, I have to make the numerator to look like the denominator and to simplify back to the numerator. So since the denominator is x plus 1 and the numerator is x, I need to first of all add the 1 to x in the numerator, then I subtract the 1 later, and then I separate them like this. So I now get something like this. Integrating now is not a big deal. You just need to integrate using basic integration techniques. Okay, alternatively, we could let u to be x plus 1. Our du is going to give us the x, so it means x is going to be equal to u minus 1. So that integral becomes this integral, and then now we can split the integrals together. We have u on u minus 1 on u. U on u is 1, then minus 1 on u. If you integrate, you get this. But what is our u? Our u is x plus 1. So at the end of the day, we see x plus 1 minus ln x plus 1 plus a constant. But the first integral here gives us x minus ln x plus 1 plus a constant. So there's something we have to see. We have to remove the 1 from the first term. We add it to that constant, and then we generate a new constant. Okay, because 1 is a constant, c is a constant, so c plus 1 is a constant. We can now call it k. So it means that integral is equal to x minus ln x plus 1 plus a constant. We are still on the principle that the result of an indefinite integral is independent of the method displayed, provided the right substitutions are used. Okay, 6 days to go. Day 15 of the integral challenge was on March 22nd. We had to integrate from negative pi ln 2 to pi ln 2 of sine x times the infinite sum from 0 of cos nx divided by n factorial. So this integral was created by myself. So let us see how I did to create the integral and how it's going to be integrated. Alright, so the first thing to note is that cos nx is actually the real part of e to the power ix, or that raised to the power n. So you just have to replace that there, and then now so e to the power I x to the n divided by n factorial, that sum is simply equal to e raised to the power ix, because we know that this has to be explained. Okay, this is what I'm trying to say. We know that e to the power x itself is actually equal to, or in fact, I don't know if I explained it, but I think I did so in the next slide or in the next upcoming. Okay, exactly. So let's get it now from here. If you've never understood this, let me explain here, and then from there you're going to pick up and you understand. Alright, so the question is, why is it that cos nx over n factorial is actually e to the x cos of sine x? Why? This is why. We have seen that the sum from n equal to 0 to infinity, in fact, the cosine of nx is actually the real part of e raised to the power I nx. Okay, so you just have to replace that in that integral. But now we know fully well that the sum of x to the n divided by n factorial is e to the x. That is the Taylor series expansion of e to the x written as a closed form. It's a sum of infinite, it is an infinite polynomial. Okay, the sum of infinite polynomials actually. So that is a closed form of e to the x from the Taylor series expansion at 0, which we call the Maclaurin series expansion. So from there, we clearly see that if our capital X is e raised to the power ix, it therefore means that this will give us e, which is the original base, but I need to replace the x with e to the ix. So you have e to the ix. Okay, look at those two sums perfectly. You just see that the n's in the power and the n factorial are there. What is just changing is the e to the ix to x, to capital X. So it therefore means that the real part of this sum is equal to the real part of e raised to the power cos x plus I sine x, because the e to the ix in the power is simply cos x plus I sine x, but the base itself is e to the is e. So e to the ix is e to the cos x plus I sine x. So from there now, we now separate it into the real part of e to the cos x times e to the I sine x. But we know fully well that e to the I sine x, the sine x becomes the argument. So we have cos of sine x plus I sine of sine x. If you take the real part, you're going to get e to the cos x times the cos of sine x. So from there now, that's the real part. Then this integral from negative pi ln 2 to pi ln 2 becomes integral from negative pi ln 2 to pi ln 2. The original integrand had sine x. We now multiply it with this sum, and then now if we look at the function g of x equal to sine x, the cos of sine x e to the power cos x. If we want to verify the parity, we are going to see that g of negative x is simply, you need to replace x anywhere you see negative x. In fact, if you simplify correctly, you get g of negative x to be equal to negative g of x. So the function g is an odd function, and since it's an odd function, then that integral is 0. We saw that property. Integrating from negative of a bound to positive of the bound of an odd function gives us 0. Okay, day 16 of the integral challenge is what you see. Sorry, this was not animated. So anyways, if you arrive at any slide that is not animated, you can just screenshot if you're interested, or you just look at it. Like I said at the beginning, that if you need the PDF, you can get to me and I'm going to share it with you. Alright, day 17 of the integral challenge was on March 24. How many days to go? 4 days to go now. Alright, so there was a quote which says, to fully understand integral calculus, you need to understand every chapter in mathematics. The next quote, there are a lot of mysteries behind indefinite integrals, and it takes patience to realize them. So I realized so many when I was doing this integral challenge, okay, because I was finding some methods, I was trying to create some integrals, I was finding short methods and very unique methods of solving integrals, not standard methods that are already known. So this integral is integral of 1 on sine x plus cos x all that squared. So follow the method I used here. So first of all, sine x plus cos x all that squared, the reciprocal is the same as the reciprocal of sine x plus cos x all that squared, which you can see. So it is equivalent to, now the denominator can be written as root 2 the cosine of x minus pi ln 4. Sine x plus cos x, in fact, you have to write in the form r cosine of x minus alpha. If you have difficulties in writing in that form, check some videos on this channel. It's going to help you to express it in that form. Now if we actually square it, we are going to have 1 on equal to all squared, which is 1 on 2. 1 on cos squared x minus pi on 4 is sec squared x minus pi on 4. So that integral is the same as the integral of sec squared x minus pi on 4, which standardly you need to have what? Half tan x minus pi on 4 plus a constant of integration. Very short. We know that tan into x minus pi on 4, the identity of tan a plus b, you can use it there. I don't know if I used another method. Okay, I used an alternative part. Where's the alternative part? The alternative part is expressing, in fact, squaring the denominator. You have cos squared x plus sine squared x plus 2 sine x cos x. But we know that cos squared x plus sine squared x is equal to 1. Okay. And then sine x cos x is equal to sine 2x. Now, if we use the half angle identity where t is equal to tan x, because here we have sine 2x, we simplify and then we just have to simplify. And at the end of the day, we arrive at this response. Alright, day 18 of the integral challenge was March 25th. Same quotes: to fully understand integral calculus, you need to understand every chapter of mathematics. There are a lot of mysteries behind indefinite integrals, which takes a lot of patience to realize them. Now we are integrating e to the x plus e to the x. Okay, so e to the x plus e to the x can be written as e to the x times e to the x. From the laws of indices, we have to add the powers. So from there, this integral becomes this other integral, which is e to the x times e to the x. We can now use the u substitution with the y substitution, y equal to e to the x. Our dy will still give us e to the x. So this integral becomes integral of e to the y dy, because the e to the x becomes e to the y, and then the e to the x dx becomes dy. Integrating, we get e to the y plus a constant, but our y is e to the x, so we need to have e to the x plus a constant of integration. Always, there is always an alternative part. It is very interesting. Now let us see a different way of integrating e to the x. Okay, how do we integrate e to the x? Using the summation. Now we already saw that the Maclaurin series expansion of e to the x can be written in the closed form as the sum from 0 to infinity of x to the n over n factorial. Now from the convergence theorem, we can switch the sum and the integral. So it's going to give us the sum from 0 to infinity of the integral of x to the n over n factorial. Since we are integrating with respect to x, then our n factorial is a constant. If we integrate x to the n, we simply get x to the n plus 1 over n plus 1. Forget about the constant of integration, it's not needed. Okay, so from here, this is when I'm now adding the constant of integration. So we now have to sum. Remember, the denominator n factorial into n plus 1 is simply n plus 1 all factorial. Now you clearly see that x to the n plus 1 divided by n plus 1 all factorial, summing it simply gives you e to the x minus 1, then plus a constant of integration, which I never put there. Okay, so from there, negative 1 plus a constant is a constant, so we have that integral works, e to the x plus a constant of integration. So when we integrate e to the x, we get e to the x, and this is another alternative method of doing that. In fact, it's actually kind of a proof of doing that, because we know that when we integrate it, it is standard, that is e to the x, because when we differentiate it, we get e to the x. Maybe you might be asking yourself why this sum is e to the x minus 1. Why is it like that? So we know that e to the x is summing from 0 to infinity of x to the n plus 1 divided by n factorial. Now we are now summing x to the n plus 1 divided by n plus 1 all factorial. Is left onto you to identify it in terms of e. Okay, in terms of e, and then now you try to simplify. If you look at it very well, you see that if you let capital N to be n plus 1, it means you're going to be summing x to the capital N divided by capital N factorial. But now you're not going to be beginning from 0, because if capital N is equal to small n plus 1 and small n begins from 0, it means capital N will begin from 1. So you're now beginning from 1 to infinity. So it means beginning from 1 to infinity is the same as beginning from 0 to infinity and then subtracting the first term. So we have e to the x minus 1. Okay, day 19 of the integral challenge was a very technical integral as well. Okay, so we dive straight away by letting u to be x plus 1. Du will give us 1 on x plus 1 on x plus 2. Our du gives us 1 on x plus 2, all that squared to x. So this integral can be written in this form, where what is inside there is u to the power 2021, and then du is what we have already. Integrating normally and replacing back u, we get what we have plus the constant of integration. So it is very straight and direct, but you need to be very keen and technical to be able to see this substitution. Critical thinking is an art. Alright, day 20 of the integral challenge was March 27. We have to integrate those bizarre things of square root again, but this time around we're taking square root of cube root, fourth root, fifth root, and so on and so forth. So like we do before, we let it to be y, and then now we can try to write it as this. For the first x, it's just raised to the square root, so it's raised to the half. For the second x, it is now a cube root, which everything is still under the first big square root, so you need to multiply half and 1/3. For the third one, you have to multiply half, 1/3, and 1/4, and so on and so forth. So at the end of the day, applying this is, we need to add a pass because they have the same base. Now you clearly see that the numerator is 1, but the denominator is n factorial. Okay, n is beginning from 2. If n is 2, 2 factorial is 2. If n is 3, okay, if n is 3, 3 factorial is 6, which is 2 times 3. If n is 4, 4 factorial is 2 times 3 times 4, because times 1 you can just remove the 1. And we already saw previously that the Taylor series or the Maclaurin series expansion of e to the x was in a closed form, was a sum from 0 to infinity of e of x to the n on n factorial. Here the x is just 1. Here you have 1 to the n, and we are beginning from 2, so you should have e minus 2. So that is the value of that sum. So from there, that integral becomes the integral from 0 to 1 of x to the e minus 2. E minus 2 is a constant, so to integrate it, we have to take e minus 2 plus 1 in the denominator, and then in the power of x, 0 to 1, and then we simplify to get 1 on e minus 1. And finally, the last day of the integral challenge was to give the value of n such that the two integrals are the same. That was March 28. So the integral from 0 to 1 of x to the n, we know it. Integral from 0 to 1 of x plus 1 to the n, we have it. We now have to equate both integrals, and then we try to solve for n. Our n is going to give us 0, because 2 to the power 0 is 1. So it is very direct forward. So guys, we come to the end of the integral challenge, the 21 days integral challenge. Do well to share the video if you love the video. Like I said, I'm going to put my contacts in the description, so that if you need the PDF of this presentation, you're going to get to me, and I'm going to give it to you for free. Okay, So thank you once more for watching. So this one, like this, I don't know, is written there day X, but it was actually day 12. It was actually on March 12 where I think somebody tried to send me an integral to challenge, and then I was trying to present a solution and I share with the person, things like that. In fact, I was trying to integrate that xe to the x stuff, I think using Maclaurin series expansion. But anyways, that's it. Thank you very much.